Lesson 1. Single Layer Perceptrons. To follow along with this lesson, you will need a solid foundation in algebra as well as some basic knowledge of linear algebra. In a perceptron application, we begin with a situation like the following. We have a set of points classified into two groups. Here we show the points from one class in green and the others in red. The objective of the perceptron algorithm is to find a linear boundary such that the points in one class are on one side and the points in the other class are on the other side, like this. The linear boundary is then used as a generalized classifier, with one side of the line defining points from one class, the green region, and the other side defining points from the other class, the red region. The line separating the regions into classes is called the decision boundary. The zero set of a linear equation defines the decision boundary. The region where the linear equation is greater than 0 is one class, and where it is less than 0 is the other class. For the perceptron algorithm, a threshold function is applied to the value from the linear function. This function sets everything less than 0 to -1, and everything greater than or equal to 0 to 1. Putting the threshold together with a linear function, we have a classification function which looks like this. The green region is where the function is 1, the red region is where it is -1. Once we have the classification function, we no longer need the set of points that we trained on. Instead, we can bring in an entirely new set of points that are not classified. Then we can apply the classification function on these points and classify them, like this. Neural networks have numerous applications, such as analyzing stocks. We might wish to program a neural network to tell us whether we should buy or sell a particular stock. In order to analyze stocks like this, we need to come up with some reasonable criteria for parameterizing the stocks. We might use the return and percentage change in volume from a prior period and set buy and sell classifications at a 5% gain or loss respectively. As another application, we might want to analyze medical images and classify whether a tumor is malignant or benign. We might use criteria like size and color to classify the tumor, like this. We can use a perceptron to classify data of any dimension, as long as the training set is linearly separable. Here we show a diagram that represents the classification function as a neuron acting on four-dimensional data. We can visualize the classification function as having several steps: input, multiplication by weights, summation, thresholding, and output. Of course, all these steps can be written in one classification function like this. The pseudocode for training the classification function looks like this. As stated before, we begin with a set of classified points. We initialize the weights to 0 for simplicity and execute the outer loop until all the points are classified. The inner loop runs through the classified points designated as P of I. Inside the inner loop, we calculate the classification. For the purpose of illustration, we will assume some values for the weights, the current point, and the classification. Here we put the one that we showed in the inputs as a component of the point. This value is called the bias, and it gets multiplied by the weight W4. The x's are the components of the point P. Class I is the class of the point. In the lower half, the linear function is evaluated to 3. After thresholding, this value is 1 in our classification function, so the point is misclassified. The next if statement checks whether the point was misclassified. The point that we just showed was misclassified, so we use it to adjust the weights. Here we show that the weight is adjusted by the class value times the corresponding component to the point. This concludes the lesson.